Today we are going to explore how our universe eventually evaporates and leads to nothing. To understand how this evaporation happens, we need to first understand what is Hawking radiation of a black hole. What was the mechanism responsible for it? In 1974, the renowned physicist Stephen Hawking made a groundbreaking discovery about black holes. He showed that black holes are not stable but instead emit radiation and gradually decay over time. This phenomenon, known as Hawking radiation, is powered by a quantum process that depends on the difference in the quantum vacuum near and far from the black hole's event horizon. The popular visualization, presented by Hawking himself, describes the universe as filled with particle-antiparticle pairs constantly appearing and disappearing. In the absence of an event horizon, these pairs quickly disappear or annihilate each other. However, near a black hole's event horizon, one member of the pair can fall into the black hole while the other escapes, resulting in real particles being emitted with positive mass, energy just outside the horizon. As the particle with negative energy, mass goes to the black hole, as a result, the black hole slowly evaporates. The particle-antiparticle pairs that appear in empty space are not actual, measurable particles. They are virtual particles, which are mathematical tools representing fluctuations in quantum fields. In reality, Hawking radiation is composed of extremely low-energy photons. The actual explanation for Hawking radiation is based on the difference in the quantum vacuum between regions of space with varying curvature. The radiation is produced due to these differences, and it propagates away from the black hole's event horizon. The energy of the emitted radiation is obtained from the mass of the black hole itself. A fascinating aspect of Hawking radiation is that it is not solely emitted from the event horizon of a black hole. Most of the radiation originates within a certain distance from the event horizon, rather than precisely at the horizon itself. Additionally, the amount of radiation emitted depends on the curvature of space near the black hole. Lower mass black holes emit more radiation and decay faster than higher mass ones because the curvature of space is more severe near their event horizon. Importantly, the amount of spacetime curvature at a given distance from a mass is independent of the mass's density or the presence of an event horizon. Whether we consider the Sun, a white dwarf, a neutron star, or a black hole of the same mass, the curvature of space outside these objects is the same as long as we are sufficiently far away from their centers. Now, let's move on to the exact problem: how our universe eventually evaporates and leads to nothing. A recent study at Radboud University by Michael F. Wondrak, Walter D. van Suilechem, and Heino Falk challenges the conventional understanding of Hawking radiation. The study suggests that this radiation is not limited to black holes but should be present for all masses in the universe, regardless of the presence of an event horizon. The new study proposes that the event horizon is not necessary for the production of Hawking radiation. The event horizon serves as a boundary where radiation can be captured or escaped from, but the radiation itself arises due to the background of curved spacetime. The researchers introduce a model that resembles the Schwinger effect in electromagnetism, where particles can be created from pure energy in the vacuum of space by applying a strong electric field. The new study means that Hawking radiation is not exclusive to black holes but could occur for all massive objects in our universe. This means that objects without an event horizon, such as massive stars, the remnants of dead stars, and neutron stars, also emit radiation, and after a very long period of time. That would lead to everything in the universe eventually evaporating, just like a black hole.